Okay, welcome back. There was a slight problem then. I had to go and look after my young baby. But you can see here I've got my 4 Cartesian divers. I'm just going to pick up a pen. This is the first situation. If we remind ourselves, it's a Cartesian diver floating stationary at the surface. So I'm just going to change some of the colors on my pen because I'm going to draw the water level. Remember, this is floating at the surface, so here is the surface of the water. Inside your Cartesian diver you would have a level of water as well. I'm just going to represent this bit here. This is the air that's trapped inside the Cartesian diver. So let's draw some forces. The first force, if I draw a dot there, is going to be my weight acting downwards. And the force that is balancing that particular one, I'll draw that one red. I'm just going to erase that because it's not long enough. It should be the same length as the weight. That's about right. And that is going to be the upthrust. You can see that they are equal in length, opposite in direction. So my Cartesian diver is stationary. It is not accelerating. Okay. Number 2, the second situation. Second situation is Cartesian diver neutrally buoyant in the middle of the bottle. So you've squeezed your Cartesian diver. I'm just going to draw I should have all these pens available really. I'm just going to draw the surface here because it's neutrally buoyant in the middle of the bottle, so the surface is up here. Now, because you've squeezed the bottle, some of the air is compressed inside the Cartesian diver and the water level has gone up. You can see here it was this depth and now you can see here it's this depth, which means that the weight of the Cartesian diver has increased. So if I use green again to represent the weight acting downwards, this line is now bigger than this line. Let's say this could be 2 newtons and this weight here could be 2.5 newtons. The upthrust. Now what's happened to the upthrust? Well, if it's neutrally buoyant inside of the bottle, then it's not moving. So the upthrust, which I represented by red before, must also balance the weight, 2.5 newtons. Now the upthrust has increased because there is a greater proportion of the Cartesian diver underwater. The upthrust on any object is determined by the volume of the object that is underwater. So in this particular situation it was 2 newtons and now 2.5 newtons. Okay, diagram 3. Cartesian diver sinking faster and faster, accelerating. Now you should know from the work that you've done before on forces that if something is accelerating, then there must be a resultant force on it. This is number 3. I definitely need to get a blue colour on my quick access toolbar. Let's go for weight. Now if it is accelerating, that weight must be greater than the upthrust. 2.5 before, let's make this one 2.8 newtons. The maximum upthrust I can obtain is 2.5 because I've got the maximum amount of my Cartesian diver underwater. So let's pick red, and the red one was upthrust, and that was 2.5 newtons. You can see that 2.8 is greater than 2.5. There would be a resultant force of 0.3 newtons acting downwards and it would accelerate downwards. Okay, let me just draw in the water levels inside there and put in my air. The air is still there, it hasn't gone anywhere, it's just been compressed. The third fourth force diagram is the hardest. Cartesian diver stationary at the bottom. So I'm just going to draw the bottom of my container and get in my colors. If it's stationary at the bottom, then there's no resultant force, so the forces must be balanced. That weight of 2.8 newtons is still going to be there, 2.8 newtons. I should put that in brackets, label this one weight. And the upthrust is still 2.5 newtons. Upthrust 2.5 newtons. But there must be a second force, well not a second force, a third force to counteract the difference between 2.8 and 2.5. Do you know what that force is? It's the force created by the bottom of the bottle pushing upwards on the Cartesian diver. And I'm going to draw this one in black, and I'm going to add it there, just to the top. In fact, I'm not going to add it there because it gets in the way of the other diagram. I'm going to add it here, and this one is called the reaction force, and it would be a value of 0.3 newtons, such that weight equals upthrust plus reaction. And this one, weight equals upthrust. In this one, weight equals upthrust. And in this one, the weight is greater than the upthrust. Weight is greater than upthrust. What I would like you to do in this assignment, I will send you a blank of this table, and I would like you to draw these force diagrams in these spaces and upload as an assignment. Thank you very much.